Pending? Yeah, okay. Works. Cool. So, shall I start?
Sure.
So, I'll be presenting the paper Dynamic and Adaptive Calling Context Encoding. And the slides in this paper are not mine. And they belong to the original authors, which are right there. So, I'll start the paper. So, well, let's start with the introduction. What are basically calling context? Calling context is when you call a function, the function gets stored on the stack. If you call another function, the function gets stored on top of the other function on the stack. So the thing in the stack is called a calling stack. So that's the context, and that is called the calling context. As you can see there, the sequence of active functions on the calling stack. So now, why do we use calling context? It's used for various purposes like testing, debugging, program analysis, and security enforcement. Moving on. So we did this the other day in the profiling lecture. So this is a very basic algorithm that's called the ball-Lars path encoding algorithm. So this encodes the paths with an integer. Is that it has accurate calling context, low overhead, everything seems nice about it. But there's a problem with it. Can anyone guess what?
Can I first ask if there's a difference between using this ball-Lars algorithm for calling contexts versus for path encoding of a control flow graph?
Is there a difference?
Yeah.
I don't know, maybe not.
So it's in part a question of where the path is going from and where it's going to.
Okay.
So if you're looking at the ball-Lars stuff, you're encoding the paths from essentially any given node down to the exit, right?
Okay.
It only works for acyclic graphs?
Well, it still only works for acyclic graphs. That's fine. That's still true here. In this case, though, we're looking at the paths from any individual node up to the, or all the different paths from any individual node up to essentially the root. Yep. So it's kind of any other.
It's kind of other way around.
Yeah.
Yeah. So anyone has any suggestions on what could be wrong with this algorithm? Okay, let's see. So the thing is that it uses the static encoding method, which works only on the complete graph. We need the complete graph to encode the whole thing in this case. And it is not able to handle dynamic loading and virtual dispatch, which we will see later on in the paper. And it needs profiling runs to identify the code and the hot edges, the edges which have been, executed again and again. And then it's not efficient in encoding space. Moving on, so that's our goals.
And can you maybe explain what some of those things mean?
Yeah, so I'll go on. And
Okay.
These will be covered as we cover this algorithm. The algorithm will solve all of them.
Okay.
Most of them. So that's our goal. So first, we want to design an algorithm that does not need extra profiling runs, because the case may be that when you are doing profiling runs, it may be extra burden on the developers to do that. So the second thing is false positives. False positives means that when you're profiling runs, it may be that the runs that you execute during your profile, they might not be executed during your actual execution. So it might be encoding paths which do not even execute, right? So then it should handle dynamic loadings. By dynamic loadings, we mean that sometimes we call a shared library. So there are functions in the shared library. So if you call a function in the shared library, if you call a shared library, all the functions will be put into the call graph. So that makes the call graph huge. Moving on, we want our encoding algorithm not to interfere with the compiling optimization. What this basically means is that when we want to do some instrumentation, we include the code in the source code, right? We instrument the source code. So the first part is that the source code is not easy to get for a commercial software. Then what can be the alternative? The alternative to this is that we can do binary instrumentation, which means that we can take the binary and we can instrument the binary itself with the code that we want. Then it should be efficient in encoding space and time. the same thing we talked about with the false positives. So what what profiling does is that it tries to execute all the call paths and tries to identify the hot and the cold edges, which means that it tries to identify which paths have been taken frequently. So that's what our algorithm should do. Well, moving on, how to handle the new call edges? Well, they could be indirect call paths or dynamic loadings. How to handle these, we'll see in a bit. And then how to ensure that the path IDs are correctly decoded. Well, the thing is, as I said, if you're encoding a path based on a particular input, you've identified a set of call paths that this is going to be executed. If the input changes, the paths taken might change. So how do you handle that? That's what this point says. Well, let's see, we talked the other day about, this is just a brief overview. It just says that there are some paths which are already encoded. They're encoded with numbers existing from 0 to the maximum ID. If you encounter something that's not encoded, it will take an ID which is between this range, maximum ID to this range. That's just the encoding numbers. So moving on, I'll give a brief overview of how the encoding is actually done. So the thing is that in case of this algorithm, every time we start with the main function, right? And then we instrument the main function to call the RT handler. RT handler means the runtime handler. We replace all the function calls with the RT handler. Now, it's actually the RT handlers that does most of the work. It does two things. First, it will add the edge to the call graph. And secondly, it will instrument the code and up in that edge. So what exactly do I mean by instrumenting? So instrumenting means doing two things. What instrumenting does is it saves the current context of the edge or the function being called, saves the current encoding context. By encoding context, I mean it saves it in the form of first ID, second the call site, and third the target of it. Then it increases the ID by maximum plus 1, and then it actually calls the function, right? And then when it returns to the function, it restores the encoding context. So we'll see an example on this. So I talked about this very vaguely. So this is the exact code, what it does. So the thing is, when RT handler is called, it instruments the code. The instrumentation is done with this. Initially, the context that is currently there before calling the function, it saves it in the stack. That's called the stack helper, which, as I said, is the ID, call site, and the target. Moving on, it increases the ID to max plus 1. Anyone can tell me why does it do max ID plus 1 exactly? Can anyone help me with that?
Because we have not encoded one.
Correct. So as we saw here, the call paths which contain newly identified edges, they'll be encoded with max ID plus 1.
Can you explain what max ID is?
Okay, the max ID is the currently existing ID, in the sense that the maximum ID of any edge, we encode the certain edges with IDs. Oh, yeah.
So from any one of these functions in the call graph, any node in the call graph, it's going to have a set of essentially IDs for all of the calling contexts that represent calls to that function.
Yes.
And the max ID is just the maximum ID over all possible call paths in the call graph.
Yes.
So if you think about this in the context of going in the other direction for vol Laris, right? You'd end up finding a maximum ID once you computed backward all the way up to the actual entry point to the function.
That's the max ID.
Right, that would give you the maximum ID, the maximum number of paths down to the exit. Going in the other direction, well, we don't necessarily have a single entry point. You know, we've got all these different positions in the graph, which might be leaf functions. And as a result, it means that we have to consider the maximum over all of those of the actual IDs.
So, the max ID, if it covers all paths, then how are we finding any new paths? How do you add one?
So when you find a new path, the ID changes to maximum ID plus 1.
But I thought max ID covered all paths.
All paths that have been encoded.
Okay.
So the key difference here then, which I think might have been a little unclear, is that you don't build the whole call graph up front.
Yep.
You start off by saying, I've only seen these functions, we've only got a call graph that represents them. As you encounter new functions, you'll try to grow the call graph.
So as he said, all the call graph grows as we call more functions. So now the newly invoked edges are not encoded immediately. So what it actually does is they are only encoded when two conditions are satisfied. The first one is when the newly added edges exceed a certain threshold. Then the whole thing is encoded. Second, when the frequently executed call paths are not encoded, the whole call graph is re-encoded. What second line means is that when, well actually I would like to discuss this. I was not clear on this. So what I think is that if we consider, like, if we are going from A to D, then to A again, then A to D, if you're going from A to D again and again, so we see that that's a frequently non-encoded path, but it's being visited again and again. So we might want it to be encoded. Is that it?
Sure, sure.
Is my understanding correct?
To the extent that they explain it.
Yeah.
There are a few things in the paper that are not presented in detail,
Okay.
to put it mildly.
Do we want to discuss on this?
We can. I mean, do people disagree about that
What do you
issue?
guys think that-
For those of you who read the paper?
So when I encountered these lines, yeah, I couldn't understand when is the threshold, how they detect.
Right.
So what if the function is indeed been called only once, but does it automatically exceed threshold or not? I couldn't understand either. Like, you can realize, right? You have main function, and the main function calls a whole bunch of other ones, but they might be called only once during the execution. So, yeah, it is indeed unclear.
What's the difference between the 2 points? So newly added edges exceed the threshold, so the newly added edge is getting used a lot. The second point says,
No, it says newly added edges. So that means if a function is calling some others, then there are calls after that. So like A is calling B, D is calling E, then it's calling F. So you're adding new edges to it. Right? So you set a threshold to 3, and when you have 3 new edges to the call graph, you re-encode the call graph.
okay.
The second thing says that when the frequently called paths are not encoded. So this might be that it might consider only A to B, A to D actually.
You need to have at least some criteria to decide when to re-encode. Otherwise, you'll end up encoding it again and again. That will increase the runtime significantly.
This is very, very true. The difficulty, I think, is that they're not precise about specifying those criteria.
Because they are themselves not sure about how to attack the problem.
Yeah, it depends. It depends in part on the application.
Right.
I mean, that's an application-specific thing,
Right.
where you want to tune it, and they don't really dive into that. So what we look at there is something where they're saying if the frequently executed call paths are not encoded, that means they have some notion of what does it mean to be frequent, and they don't really even discuss tracking frequency or measuring frequency in the paper, at least that I recall. Maybe somebody else noticed that and I didn't. Now that's something you see that a lot in dynamic compilation inside a JITting infrastructure. You see that, for instance, inside the JVM. So it's a fairly advanced adaptive feature. And you could even make some decision that, well, okay, some other paths are no longer frequent, let's not encode them anymore, something along those lines. Which is the sort of dynamic de-optimization you see inside the JVM as well. But they don't really dive into that. In fact, they had another, a third criterion inside the paper that's not in their slides, which is just that if you access the stack a lot.
Right.
That is the recursion.
It's presented.
Somewhere in the indirect calls or recursion, it's there somewhere.
It's presented in section 4.
It's there somewhere.
Yeah, but it's presented with the rest of these, and again, these notions are just not well defined, I would say. It's clear ambiguity.
So we will see an example of what we just simply learned. So we will take the path A, B, D, E, I, then to C, then to E, and then again to I, right? So first A, this path is already encoded. We need not do anything. Moving on to B, nothing. D, nothing. E, nothing. Since this is already encoded and this doesn't say that we are increasing the context ID, this stays as 0, right? But move on to I, this says +2. This means we need to increase the context ID. It increases the context ID to 2. So now we want to call C. Can anyone tell me what will go on the stack right now? Will something go on the stack?
No,
No.
ID will be 0.
But
I want to tell you that these dotted line means they're unencoded.
yeah, so we should put
So
it
max
on-
ID.
Add max ID plus 1.
Yeah, 3 I think.
So I can say that the two people who are answering are two people that I know have read the paper, which is an indication that the underlying technique is a little bit subtle.
Okay.
So the issue here is that you haven't seen the edge from I to C before, right?
Yeah,
It's a new edge.
it's new edge.
So, yeah.
So as we talked about, if you encounter new edge, you first save the context information onto the stack. So the current context ID is 2. Who's calling it? The call site is I.
You just add
The target is C.
I to C.
Yeah, so I'll save 2IC, which is exactly what's saved on the stack, right? Now, the ID, it was increased from max ID plus 1. So that's 4 plus 1, which is 5. That's why the ID has increased to 5, right? So now, here's the tricky part, which we'll discuss. So now, C to E is also unencoded, right? So what do you think will go on the stack right now?
It's less than max ID.
I mean, the current ID is 5, the max ID is 4. What do you think the current, what do you think will go on the stack?
6 CE.
5C.
Okay. So you say 6.
Yeah.
Actually, that was my first intuition because you increased the ID by 1. But the thing here is he's increasing the ID by max plus 1. So max is still 4. So 5 CE goes on the stack and the ID still remains 5. Is everyone clear with that? Any questions?
So could you explain why it is happening?
Because this is an unencoded path, right? So the algorithm says that you save the context information onto the stack. That is the current ID, that is 5.
Mm-hmm.
The calling function, that is C, and the target, that is E. So I save 5 CE to the stack. Similarly, I need to increase the ID after saving. So ID is equal to max ID plus 1.
Mm-hmm.
Since the max ID is 4, the new ID is still 4 plus 1, which is equal to 5. Right? Is everyone clear with that?
I to C was also not encoded, right?
I to C was encoded. No, it was not encoded. Yeah.
Then shouldn't we?
That's why we say this 2IC.
It shouldn't we use max ID?
It's fine. The
It
thing is-
used
It's dynamic analysis, right? At some point you need to change the max ID.
That's-
It was not clear.
It's, I mean,
And then-
even I thought that you should use the previous ID, but
So, the thing is that it's dynamic analysis. The graph will keep on increasing. What point do you set max ID?
that's what it says is
So
re-encodes.
there's only ever one graph at a time. So you never say, okay, I'm making a new step, I'm gonna change the graph. You have a set max ID. There's a max ID for this graph,
Right.
and you have these other dotted line edges
And that will
don't
remain
have.
same until and unless you re-encode the whole
Right.
graph. Right?
Right.
And the criteria was not clear, like when you do.
Okay, yes, yeah.
How you set the max ID.
Couldn't max ID just be set to 1?
It starts out at 0.
Okay.
Yeah. If you just set it to, if you keep it essentially at its minimum and decide never to grow the theoretical encoding space of the graph, then you're just maintaining an auxiliary stack that you push and pop onto, which is a shadow call stack. And that's just expensive to have the push and pop operations to memory every time.
Okay.
If you can reduce it to arithmetic operations that don't have to go and do all those memory ops, then it's faster.
Moving on. So the next step we need to go is from E to I. So this path has already been encoded. So it will push nothing on the stack. It will just increase the ID to 7. That's clear now? Moving on to the actual part of it. So that's the whole thing. That's how you decode the algorithm. So I'll go over the algorithm with some example. Well, the algorithm has 2 main parts. It starts off with a decode function where it actually calls the edges ID every time, once it starts. So what, okay, actually I'll move on, then I'll come back. So the thing is that the function has the algorithm has 2 parts, 2 major parts. The first part is understandable, that it says it handles unencoded call edges, right? Second part is a bit tricky, which I had trouble understanding. Like, what is this thing, ENE? Something is being done here that is very critical. But what is this thing? Can anyone help me with that?
I would provide a hint and say that that is the part that corresponds to what I showed you in class.
Yes, but
You just see it here more formally.
so, I'll give you an example. We'll decode through the example. Maybe we'll come back to it later. Is that good for all of you? Okay. So that's the whole algorithm in a gist, a small thing. It actually uses a flag on stack to indicate if there is something on the call stack. And then it calls the adjust ID function, which tells you whether this function will be executed or not. Now, how it does it is that it actually checks if the ID is greater than the maximum ID right here. And if it is, it actually subtracts the ID minus the maximum ID plus 1. So once the ID has changed and the onStack flag has become true, this function will come somewhere here. It will check if ID is equal to 0 and onStack is equal to true. That's what makes this execute this part of the algorithm. That handles unencoded call edges, right? So in each iteration of this, what it does is actually when it goes into this, it pops off the top of the stack. Now, we had 3 things in the stack. Can anyone tell me what they were? Yeah.
The target.
Yeah, the ID, the call site, and the target, right? That's written right here. ID, call site, and target. So now what it does is it actually compares. It compares the target in the call stack with the current function, with the current function that you are at. So basically, what it is doing is it's checking if you're at the right function, you're decoding the right path, the right edge. So it actually checks it right here. If 1 is equal to target. If it is true, it goes into that and tries to get the edge. That's what this function does. Now, the get edge has actually it has two types of functions and two types of implementations actually. The first type says that the stack is popped with an extra variable count, but we never saw that till now. We will see this coming further in recursion. This is called compression. We'll see that later. We currently are on this thing. The stack is popped on the top, and then it decodes. Yeah.
That's the second part.
Sorry?
That is the second part.
Yeah, that's the second part. If this was not true or it did not enter this, which is a bit unclear. We'll move on to the example and then we'll discuss this coming back. So this is where we left off, the encoding thing, right? We have the ID as 7. We have the helper stack like this. And we want to go back from I to E, then to C, then back to I, then E, D, B, and A. So this is our current status. It says that the current function is I, that's ifun, the function we talked about, and the ID is 7. So the first thing the decoding function does is, as I said, calls the adjust ID function. The adjust ID function that's right here. It will check if the ID is greater than the maximum ID. Since we talked, the maximum ID has not changed. It is still 4. Now the ID is 7. So since 7 is greater than 4, 7 will get reduced to 7 minus 5, 4 plus 1, which is 5. So the ID becomes true 2, and the onset stack becomes true. So this is all this part of this is doing. This part of the function. Is everyone clear with that?
So if you had to explain what the whole max ID plus 1 business was doing, could you like, in one sentence say what it does?
Well, it actually reduces it to the original ID, since we have increased the ID going from let's see. Since we added this onto the stack, actually we want to come back from I to C. No, that's, let me see.
It's really just a flag, is what I would say. If your ID is greater than max ID, then it's a flag, right?
So you should look into the stack.
Yeah. It's a flag saying something's unencoded.
But then you're reducing the ID too.
Right. But that's not what max ID means, or the use of max ID means. So that's an artifact of the fact that they're using this greater than max ID as a flag.
Okay.
So because they're essentially having something that could be greater than max ID, and that's just a flag for something involving something
is on the
unencoded.
stack.
Yeah, you just reduce it after that to remove the flag and figure out what the actual ID up to that unencoded part is.
Okay, that's the current situation. Now we are done with the adjust ID. We move into the loop. So we have ID is equal to 2 and on stack is equal to true. But our function requires the ID to be equal to 0, which is right here. It wants the ID to be 0 and on stack is equal to true. So since the ID is 2 right now, we don't enter into it.
Why? What does that mean?
Well, that means that it is not an unencoded pass.
Right.
That means that this part is being handled. This handles the encoded paths.
Yeah, so at a high level, the top part is stripping off or peeling off one segment at a time, or one acyclic segment at a time.
All the encodings that have already been there.
Yeah, just one at a time though.
Okay.
And then you fall into the second part and
That's
decode
what
it.
this is doing.
Yeah.
So we actually, since this is the only part that has been encoded, this is still unencoded. So we'll stop here. We'll strip only this part off from E to I, right? So only the edge EI is decoded. And as I said, this has something important to do.
So it's saying that you have an ID over there, +2, right?
Yeah.
So when you go back, you just subtract that. from the
Yes,
ID.
that is what this ID said it was important, it was doing something. This is being done here. That's what it does, ID minus En of E. So, from my understanding, this En has to do something with this value 2. Is it correct?
Yeah. So that follows the example that we did in class as well, right? When you start the decoding, when you traverse along the edge during the decoding process, you subtract that to get rid of that allocation portion of the encoding, that subdivision.
Do we do the decoding after we have followed the graph, or we can do it anytime?
You can decode at any time, but only with respect to a graph, with respect to the graph that was used for the encoding process.
Okay.
Okay, so moving on, right? So now we are on E, and the ID has become 0, right? And the current function is E ID 0, and on stack is equal to true, right? So this on stack, this becomes true. Let me see. Somewhere here it calls the adjust ID. Well, not here. So the ID, the on stack was still true since it did not change the on stack anywhere. The flag is still true. The ID has become 0. So this goes back. Stack is not empty since the on stack is true. ID is 0, but still it does not break. It goes back right here, right? So we have the ID 0, we have the on stack true. That's 2 conditions. We will move into the loop, and we'll check the stack, the top item of the stack. So currently on the top we have 5, C, and E. I said something about comparing the function, actually the target side in the call stack, with the current function that we are at, right? So the current function we are at is E, and the target at the top of the stack is also E. So that means we are at the right place. So
If you could explain that at a high level, again, like a one sentence, what does that mean now?
well, let's see.
You save the previous context.
That you decoded that acyclic segment. You
So
finished
you know
decoding
that
one
now,
segment.
right? You are
Yeah.
back to the
You're back to
less
the-
than max ID, so now you are in the context.
Yeah.
So you are in that space, 0 to max ID space now. So you do the regular decoding process, which we already did.
Right. You finished that.
Right.
You
So-
finished.
Yeah. So you decoded up to the target of something that was unencoded.
Yeah. So now we're dealing with the unencoded edges.
Yeah.
Do you want me to explain that now? So yeah, so as I said, since the ID is 0 and the on stack is true, the encoding context on the helper stack matches the entry with the current context. So the pop-up happens, which is this. If I say if fun is equal to target, then I say set the on stack is equal to false, and then I say pop somewhere it does pop. Okay, it does the pop here, right? So I pop the top of the stack, right? And then I restore. Okay. So then I pop the top of the stack, change the on stack flag to false, right? And the current ID becomes the ID that I popped on top of the stack, right? So the ID was 5. I restore the ID, right? This means that this 5 becomes the ID, right? On stack becomes false, and then we move into the same process of adjust ID again, right? We go from here back to here, right? So adjusting the ID again. So since the ID is still greater than the maximum ID, 5 is greater than 4, so we adjust the ID again, right? But this time, the last time it was 2, this time it becomes 0, right? So we enter the loop the first time, which tells us that there are no encoded paths in our way. We are still decoding the unencoded paths, Is everyone clear with that? Okay, moving on. So we restore, and yeah. So now the thing is that this becomes 0, and this function target matches the current function C. So we do the same thing. We pop the stack, restore the ID, and then go to the adjust ID again. So when we pop the top of the stack, the ID becomes 2, right? ID becomes 2, and the on stack becomes false. Is everyone clear this part? Does anyone have any doubts? Shall I go again over it?
Mm,
Do you want me to continue?
continue.
Okay. So now what is this saying? The on stack is equal to false and ID is equal to 2. This tells us that there's nothing on the stack anymore. So all we have left is the encoded edges, right? So doing the other thing, what the second function does is we'll do a -2 right here. This does a -2 right here. And actually, let's see. So, as we talked about, it will decode all the encoded paths one at a time until it encounters an unencoded path. So, while decoding this, going back to this, we don't have any unencoded path in the way. So we will decode this whole thing in this for loop. This for loop. Right? So it says that the whole path IEDBA is decoded at one go in the for loop. One path at a time. So we have this, and hence this is decoded. So the ID question.
So it was able to figure out E from I by the +2, correct?
Yeah, we had this +2 here.
Is that the only way it figures out to go to E? Is by the +2? Or does it?
Yeah.
Actually, this no, it's not the +2. It actually gets the edges from this, right? It gets each edge from this is
The way it chooses though is based on the +2.
is it?
Yeah. So if you look at the way that section, the E and E, that's what has +2 in it, right? So you've got +2, which has the bottom range of where this ID, of what this ID should fall into, and then you've got num_CCs, number of calling contexts,
That's the upper range.
which is the upper bound on the range. And since the ID falls in that range, you know that it had to fall along that path.
So what happens if there's, like, back to your graph, Fi? Is it possible to have Fi as +2, or is that not possible?
So
It's by construction. It's by construction. If one of them is +2, the other won't be.
Okay, that's what.
So from D, if you see, there are two paths, right? F, E, right? So the ID of D is 2, and since from D to E there is only one path, you add the same ID to 2, and the same goes for F. Now to I, from D to I there are two paths, right? So you take the one path from DFI as the same encoding space. So you take that path as like 0 or something. So that becomes the same ID, and the other one just adds the previous ID of F. So +2 is from the 2 of F. So it becomes 2 + 2, 4 then. For F.
So you can think about it as finding the number of possible contexts to each of the potential callers, and then just partitioning the space for each of them.
Yeah.
So that's been decoded. Well done. So moving on to indirect calls, right? Okay. So now the previous algorithms had some problems. If you had indirect calls, the call graph would grow and grow and grow. In this case, it handles it a bit differently. Okay, so what it basically does is, it's the same threshold thing. I mean, if the number of indirect calls increase a certain threshold, it uses the hash table to store the addresses of the indirect calls and the coding of the indirect calls, right? Well, so what this is all about is that now so it actually behaves as a normal call. The indirect call actually behaves as a normal call in a normal context when you don't have more indirect calls, right? So that's the same thing as we discussed. Normal encoding, decoding, nothing fancy. But if you have more number of indirect calls, they'll be saved in the hash table.
So you mean more at that call site?
Yeah, more at that call site. I mean, if it a
Different targets.
Yeah, different targets. So what it does, it saves all the targets in a hash table, as I said, with a particular hash value. Now, if it saves them in hash table, how do you access them? It instruments the code, that's the call site, with a certain hash function, which calculates the hash value based on the target, right? Now, that hash value calculated is looked from in the hash table. And if there's a match, you add the coding to the ID. That's what this part is doing. Now, if you see that there is no value in the hash table, that means the call site has not been called. So you add that to you have the runtime handler, which does the part of the adding it to the call stack. Is that clear? Well, okay, I'll go over it again. So the thing is that
I think for the sake of time, we should probably continue on so we can have more discussion of some of the evaluation and whatnot too.
okay. So that's how the encoding indirect call works. So we consider an example ACEI with a max ID 4. So the thing is that A to C is pretty straightforward. A C to E is an indirect call. So when an indirect call is made, 0, C, E are pushed onto the stack, which is the current context. So the ID becomes, since there is no encoded path, it's pushed onto the stack, and the ID becomes max ID plus 1. That's the same thing as we did in the last case. And that becomes 5. 5 plus 2 becomes 7. So EI leads to 7. So final result is ID 7, and that's what is on the stack. This is pretty much similar to the last example we saw. Decoding is in the same way. The ID is greater than the max ID. It subtracts on stack true, and then the whole thing is decoded. It's pretty much the same example, right? So moving on to recursive calls.
Skip it. Let's go to evaluation and we'll discuss it.
Okay, I have a question here. I'll discuss this recursive calls. So as we discussed the recursive calls, so the previous algorithm didn't handle the recursive calls so well. So what this actually does is, as we talk about compressing the recursive calls. So by compression, I mean, I've seen this example. This is an example without the compression. That's the normal example. This is an example with the compression. We'll have a look at this first. So if you consider the path AD, AC, DAD, when I call A from D, the path doesn't exist. The context ID is pushed onto the stack. ID becomes max ID plus 1. As was his question, the max ID was, I think, 0 in the beginning, right? So it becomes 0 plus 1, that is 1. So ID becomes 1. So next time when it goes from D to A, there's no path. The context is saved on the stack right here. And I don't know why in the paper it says that the ID remains 0. I think it should become 1. Do you agree with me? Anyone would like to explain why this still is 0? Shouldn't it be 1?
We haven't encoded yet, right?
No, but we don't have an encoded path to this, so we will save the context and push the ID onto the push the information onto the stack, and increase the ID is equal to max ID plus 1.
Yes, but we discussed before that max ID haven't changed yet.
Max ID was 0, so 0 plus 1 should be 1. Then why is that 0? My thing is I say that this should be 1.
I was a little unclear on that too. Because whenever you traverse a fuzzy edge, it means you should be setting your ID to, or dashed edge, you should be setting your ID to max ID plus 1.
Yep.
So, at least that's my interpretation too. But it's unclear. It's one of those things that in the paper, there's some conflicting information.
That was the part where I was unclear. Rest is the same thing, max ID plus 1. Because it's increasing the max ID, like it goes from D to A here, then goes 0 plus 1, that is 1. So if it's going from here to here, it says 1, then why not here? That's one of my questions. So moving on quickly to the compression part. So what the compression does is, it actually checks if the call site and the ID are same as on the top of the stack. So what do I mean by the call site and the ID? So if you see here, D is calling A. D is going to call A. But the thing is that the ID is still 2 and the call site is D. So 2DA0, it already exists, right? So why to add something again which already exists? So what it does is, if it finds the ID and the CS is same, the call site, so it increases the count. The count, as we discussed in the give edge, there were 2 cases. One was with the count, one was without the count. So this is the one with the count, in which it increases the count of this, the same thing, by 1. So that's how it becomes plus 1.
So this is essentially run length encoding of repeated acyclic segments or acyclic paths in the call graph. Oddly enough, the previous paper that this one is improving upon did the exact same thing, and the journal version actually did more.
Well,
backwards? So these guys went backwards?
They didn't look at the journal version, which I can say is one of the authors of the journal version.
Okay. So that should be another major part of the paper, but I don't know if he's just given 2 small paragraphs on this. So that's all I could gather. So that's
essentially the adaptive part just says that every now and then they re-encode everything and fix everything up. They don't say that much about it, except one of the interesting points here is that you can't do this arbitrarily. If you have concurrency or what have you, these other issues going on, you have to wait till safe
In
points.
the motivation part, they have talked about that this is much better than the static part, but they have not explained how and why.
Yeah,
When it comes to data sharing and
this is true. Now, this has potential to be adaptive in ways that the static approach does not. So you can do things like de-optimization. But they don't really do that.
Yeah, that is from the paper, the same
Yeah.
thing. So that's when the adaptive encoding call will be called, as we discussed. That's the same thing. Well, that's the same.
Yeah.
This is where I had some problems understanding.
Okay.
So the decoding mechanism, it's not that clear. It just says that everything is arranged in order to the invocation frequency. Every edge that's invoked the most number of times is given the frequency 0, and it need not be instrumented.
Given the instrumentation 0 or the ID 0, not the frequency 0.
Given the frequency ID 0. No, given the ID 0.
Right.
And the encoding 0, sorry.
Yeah.
It's given the encoding 0 if it's called the most number of times.
Yeah.
So it need not be instrumented, which saves us some runtime. So, but the thing is that it says that we have this timestamp, which the edge, what edges are there, and the number of calling contexts. So how are they able to decode from this thing?
That's the complete graph, right? You've got the edges, you've got the nodes.
Okay.
That's the graph. That's the encoded graph.
Okay.
So all it's doing is saving versions of the graph with all of those annotations. And then every time it re-encodes, it makes an entirely new graph, which could also be expensive. And you can't throw away the old version, because that would mean you could no longer decode things that you'd already encoded using that previous version. So you've got to keep track of the version of the graph that every context ID was created with. Otherwise, you won't be able to decode either.
That seems expensive.
Is that what
Potentially.
Is that what the new timestamps are from?
That's what the timestamps are for. Yeah, exactly.
So these are the results. but there was a thing I found in the results. So if you see it behaves really good here, it behaves really good here, it behaves really good here.
No,
But-
it's not good. It's runtime overhead, really bad.
Well, so,
No,
so
right?
yellow is the
The
older
new
version.
algorithm
Yellow
is
is the
behaving
old-
good. So
But
D,
yeah, it's still compared to the.
compared to the previous algorithm.
Comparatively good,
It's-
but still bad.
Yeah.
Yeah. So, but the thing is that this behaves good in this because this has a lot of, what do you call, cold edges, the edges, hot and cold edges. So this takes care of that specifically, it behaves better. Well, in this case, there are a lot of indirect calls. This new algorithm takes care of them specifically and behaves better. But in the other cases, you see it's almost same or worse than the previous algorithm. Right?
And they didn't compare against the latest version of the previous algorithm. But,
So that's,
yeah.
well, I mean, they're just they're doing better in the specific cases they're taking care of.
Okay, one question, like, how is this calculated runtime? For example, in dynamic analysis, to do a complete analysis, you'll have to run through different inputs, right? So the total runtime of a dynamic analysis includes all the inputs, or are they talking about one specific input?
So for this particular issue, this is one of these interesting cases where they're not trying to find bugs or anything like that. So they don't have to run multiple tests on multiple
Right.
inputs. They're just looking at a single input. This is a standard benchmark set where
But
you've got.
It's not serving the purpose, right? Like,
It
only
is-
for debugging.
The assumption, for instance, is that these inputs are representative enough for these programs that you'll get a good sample of the behavior of that program.
So this is multiple inputs or just one sample of inputs?
Technically, it depends on the benchmark. Some of them have one input, some of them have a few inputs. Spec is a standard benchmark scheme. But we're not trying to find bugs or something like that, for instance. So we're not trying to get a sample of representative program behavior. We're just trying to add in additional information to the runtime, which is a little bit different than some of the other analyses we've looked at, right? So we're not trying to say anything about all possible program paths. We're just trying to say, for this program path, could we encode the context? And they're able to do that. Yeah.
So, thank you. And any questions?
Other issues in the time we don't have?
Are we out of time?
We are, but unless someone kicks us out, we can ask some stuff.
I just have one. Was that the result? Was
Yeah.
that the main purpose of the paper, was to reduce the overhead?
Yeah.
I would say that it is handling dynamic loading better.
That's
So
only the part.
it's primarily just more convenient. That's my view.
Okay.
Its efficiency claims are somewhat specious, also because the previous paper also presented two algorithms, and they're only comparing against the first one, which was less efficient. And then continue with the journal version that was improvements on top of that. They're not comparing efficiency-wise in a meaningful way.
Okay.
Also, some other folks noted that, well, they look at average numbers in some cases where they should be looking at things like percentiles for doing their evaluation, and so they don't have good bounds on things like memory consumption.
Okay.
They have things which are very misleading, especially because there's a skewed distribution. So convenience. To me, convenience is the big thing. And convenience is an important factor. I wouldn't ignore that. I think it's an elegant, in some ways, approach.
Mhm.
I think the approach that we presented in the older papers introduced dummy edges in places where they're using this max ID system, which I think is cute. It's a little bit more elegant.
Sure, they're cute.
Look, it's aesthetically pleasing.
Yeah.
Which is something to be said. I mean, that's
Well,
good.
That's where it seems like the contribution of this paper is its usability, and it makes it
I-
better graph.
I think that would have been a much better argument, or a much stronger argument. Because the arguments that they made are not entirely true in many places.
And not entirely good.
Yeah.
But in the conclusion, it didn't claim that they actually improved by reducing the overhead. It was claiming that it was adaptive and.
This is true as well. I mean, technically, the static approach also can handle dynamic loading. It's just you have to pre-compile the things that you're going to dynamically load ahead of time. This is just more convenient. And even when they talk about things like encoding space.
Uncomputed graph. That was the 2 point that it is adaptive and works on uncomputed graph.